Hi everyone, hope you all are sound and healthy. Myself, Ambily, I am currently pursuing my Masters in Space Physics at Andhra University. Today, I'll be talking about magnetic mirrors and magnetic bottles. Let's have a look at the topics. Here, I'll be discussing about the motion of a charged particle in a uniform magnetic field as well as in a converging magnetic field. Then we have the magnetic mirror configuration and its parameters. We'll see how a magnetic bottle works. Then I'll be talking about the radiation belts around our Earth. After that, we have the International Thermonuclear Experimental Reactor, ITER. And finally, we'll have a brief discussion about the numerical modeling on this topic. So let's begin. When a charged particle is placed in a uniform magnetic field, it will experience a magnetic Lorentz force, which can be defined as F is equal to Q into V cross B, where V is the velocity and Q is the charge of the particle. As we can see in the equation, magnetic field is perpendicular to the velocity. So, the velocity changes its direction, but not magnitude. The result is a uniform circular motion, where the particle's kinetic energy and speed remains constant. The radius of the circular path is given by r is equal to mv by qb, where m is the mass, v is the velocity, and q is the charge of the particle. Since here the particle shown has a negative charge, the force will be in the opposite direction to the prediction of right-hand rule. So, if the velocity is not perpendicular to the magnetic field, then the particle will follow a helical motion. The velocity component perpendicular to the magnetic field, that is v sine theta, creates a circular motion, whereas the velocity component parallel to the magnetic field, that is v cos theta, moves the particle along the straight line. Here, the pitch is the distance, horizontal distance between two consecutive circles, which is given by the relation pitch is equal to v parallel into t, where t is the time period. However, motion of a charged particle in a converging magnetic field is another case. Let me show you a small demonstration of this. So, the particle will spiral around the cone of converging field lines. Particles approaching the ends will experience an increasing force that eventually causes them to reverse their direction. By the laws of motion, any force can be resolved into the sum of mutually perpendicular forces, each controlling the motion in its direction. The radial force will keep the particle to turn in a circle around the axis and is balanced by the centrifugal force of rotation. The parallel force, which is a small force, will repel the particle away from the tip of the cone. That added force gradually slows down the particle's advance along the axis and reverses it, causing it to the mirror effect and bounce back. Here we are assuming adiabatic invariance of magnetic moment, that is, the particle's magnetic moment and total energy do not change. But adiabatic invariance is lost when a particle occupies a null point or a zone of no magnetic field. In region with no magnetic field, if the total energy remains constant, then the velocity parallel to the magnetic field must drop. If it go negative, then there is a motion repelling the particle from the dense fields. That is what happens in a magnetic mirror. It is a device used to confine charged particles such as plasma. One of the simplest way of this is to construct a parallel magnetic wall around the plasma column. In this configuration, usually electromagnets are used to create an area with increasing density of magnetic field lines at either end of the confinement area. Let's consider that the magnetic field is along the z direction. Then the component of velocity, the z component of velocity, decreases as time evolves. So the particle gets decelerated, and at a particular time, the Vz becomes 0. That time is given by t is equal to 2v1 over alpha v0 square, where v1 and v0 are the velocity and zero order perturbation of particle, and alpha denotes the convergence of the field. At this time, particle comes to rest position and reflect back with increased velocity along z direction, which is not equal to the initial velocity and is different for different particles at different points in the same magnetic field. This is known as magnetic mirror configuration. It is satisfied for normally low density plasma having high temperature. Now, let's discuss some parameters of this configuration. So the mirror effect will occur only for particle within a limited range of velocity angles of approach, and those outside the limits will escape, making the mirror inherently leaky. So the first is the magnetic mirror ratio. So the magnetic mirror themselves have a mirror ratio which is expressed as R mirror is equal to the maximum value of magnetic field over the minimum value of magnetic field. It should be always greater than 1. And the probability that the particle escape the mirror is inversely proportional to this ratio. It was expected that smaller magnetic field would reflect less particles and heavier and faster particles would be harder to reflect. But in any case, magnetic mirror ratio required remains the same. Next is pitch angle. So it is the angle between the velocity vector and the magnetic field vector. Here is the equation for the pitch angle. Here theta is the pitch angle and sine square theta is equal to the minimum value of magnetic field by the maximum value of magnetic field. And surprisingly, particles with small pitch angles can escape the mirror, and these particles are said to be in the Lowe's cone. So you can see the Lowe's cone in this image. Here the particles who have the angles greater than theta naught will be trapped, and the particles having the angle less than theta naught will be lost. So next is the magnetic bottle. Two magnetic mirrors can be arranged to form a magnetic bottle that can trap particles, charged particles in the. So two parallel coils separated by a small distance carrying the same current in the same direction will produce a magnetic bottle between them. The particle acts as exactly same as that in a converging magnetic field. It is to be noted that the magnetic field does no work on the trapped particle in the magnetic bottle. It just changes their direction. It is the velocity of the particle itself and the force in the axial direction which causes the oscillation. It is easier to trap electrons than ions because electrons are much lighter, and this technique is used to confine high energy plasma in fusion experiments. So here the Vz will provide the pitch for the helical motion, and the Vx and Vy, the other component of velocity, will contribute to the circular motion as that in a converging magnetic field. Now we will see a practical example of this magnetic mirror. So we all know that the Earth acts like a giant dipole magnet, and its magnetic field lines converge at the magnetic north and south poles. In a similar fashion of a magnetic bottle, Earth's non-uniform magnetic field traps a charged particle coming from the Sun in a donut-shaped regions around the Earth. Particles move to and fro continuously between these poles. The region of 1.5 RE and 3.5 RE are those where the particles are trapped and radiate energy, taking RE as the radius of Earth. It was discovered by James Van Allen and thus named as Van Allen radiation belts. In fact, it was Van Allen was measuring the flux of cosmic ray particles on Earth to see whether this was similar to the flux measured on space. He found that due to the contribution of particles trapped in the magnetic field, the flux was much higher than in outer space. Later, the in-space missions on Explorer 1 satellite observed more about this amazing phenomena. Now let's go more deep into this Van Allen radiation belts. The inner belt or the proton belt is located at nearly 1000 to 8000 miles protons with energies greater than 10 megavolt. Current studies reveal that these protons are trapped cosmic ray particles from outside the solar system or from the sun itself, possibly during severe solar flares. There is also a low energy electron belt which actually overlaps the volumes of proton belt is located. These electrons carry 1 to 5 megavolts of energy on average. The high energy electron belt is located further out than the two overlapping inner belts. Electrons in this belt vary between 10 to 100 megavolts of energy. Natural phenomena such as the aurora borealis and aurora australis, commonly known as northern and southern lights, are beautiful displays of light which occur when the charged particles from their Van Allen radiation belt. Light is emitted as ions recombine with electrons entering the atmosphere as they spiral along the magnetic field lines. The ions are primarily oxygen and nitrogen atoms that are initially ionized by collisions with energetic particles in the Earth's atmosphere. And magnetic mirrors, used as an efficient tool to confine plasma, has been widely adopted in many, such as plasma thrusters and fusion research. One example is the International Thermonuclear Experimental Reactor, ITER. Although magnetic mirror configuration has the the advantage of having no dynamic instabilities such as those in a presence in a pinch effect, it has yet such an essential disadvantage that the charged particles can escape freely from the confinement region, where the magnetic fields are straight and the region has finite ends. So to produce hot plasma efficiently in any reasonable length of the system, magnetic mirrors are arranged in an end-to-end circle. And this toroidal configuration allows to control plasma and is used in ITER. It uses this configuration to generate thermonuclear fusion power that uses magnetic field to confine plasma. And India is also taking a project under the Institute for Plasma Research, IPR, in Gujarat. And let me walk you through numerical modeling, which I have done as a part of my master's project. So the work mainly aims to model the path of a charged particle in a converging magnetic field as in a magnetic mirror. It is written as a computer code in Python, which numerically solves complex differential equations using Euler's method. These are the equations of magnetic field present in the simulation along x, y. Here, m is a constant which decides how much this convergence affects the motion of the particle. Also, C is introduced for describing the magnetic cloud size in the simulation. The simulation was run with varying values of C at a definite step size until the reflection is obtained. So here is a visualization of the program flow used in the implementation of Euler's method for this study. First, we input the initial values for f of x, is the x by step size, and compute its derivatives. And if needed in a complex problem, we can compute and update up to n, and then save all the values like f of x and its derivatives to its disk, and check whether the value of x is greater than the end value of x. If it is false, you can return to this step, and if it is true, load all the values, all the data, like the user defined functions and all, into the memory, and then output for the plotting, and then plot the data and values with library of your choice. Here I have used matplotlib. So the results are shown here. The path of a charged particle in a magnetic cloud as well as in a magnetic mirror obtained through the simulation are given here. Both the graphs show three-dimensional visualizations. In the first graph, we can see that the particle is spiraling along the magnetic cloud. Here it is the x, y, and z axis. And in the next graph, we have this axis, and one can see the particle is getting reflected off this magnetic mirror. So the axis values are constrained according to the size and strength of the magnetic mirror. Shows the path of the charged particle in a magnetic mirror. And here are the references from where I have collected the data. This is textbook Plasma Dynamics by Boyd and Sanderson, which is a very useful guide to plasma dynamics. And some of calculated from the NASA website. And these two other research articles describe mostly about a magnetic mirror configuration and its disadvantages. And this one talks about the Van Allen radiation belts. And that's about it.